Hi everyone, welcome to my class. Today we will discuss on pulse code modulation PCM. So the objective of this lesson is at the end of this course you will be able to explain the concept of PCM and solve problems involving PCM. So let us give a little bit more focus on PCM. This is the most commonly used digital modulation scheme. And each sample is represented by binary numbers representing in terms of bits 0 and 1. And then how many bits will be there? It depends on how many levels of amplitudes are used for Fourier. There are two types of PCM, linear and nonlinear. Linear, the levels or the voltage levels are separated by equal voltage gradations. So in linear PCM, there are two types, unfolded and folded. We will more focus towards unfolded one and little bit discuss about folded one. Okay, now let's about nonlinear PCM. Nonlinear, the voltage levels are not separated equally, they are unequal. Okay? The voltage gradations are unequal. Let's see example. This is uniform. You can see the level, the voltage difference are uniform. Whereas this one, where the signal more dense in the area, the voltage levels separation are very small, so that can be captured all the variation of voltage level, whereas they are very less, means like turning points where there is a change and variation, but where not much change, the voltage level differences are more. So this we use in terms of quantizer, non-uniform quantizer, unequally spaced level. Whereas for uniform quantizer, linear quantizers, voltage levels are very equally spaced. Okay. So what are the uses? What are the use of non-uniform or non-linear quantization? Non-linear in terms of non-linear PCM. Okay, to improve the signal to noise ratio, okay, they are used. So more levels is available for low level amplitude where there is turning compared to high level amplitude. This can increase the signal to noise ratio for low level amplitude and decrease signal to noise ratio for high level amplitude. Okay. Here, two things are done, compression and expansion. So analog compression is done to the input signal before sampling, okay, and quantization at the transmitter. Expansion is done at the receiver. So together compression and expansion is known as compounding. Okay, but non-uniform PCM, okay, utilizing non-uniform quantizers are difficult to implement, and it is expensive. So linear PCM is mostly used. Now we will go for linear PCM. There are three steps as we discussed our previous lessons. To do the PCM, sampling, quantization, and encoding. So we have to sample the signal with a equal interval, and then we are focusing on PAM, pulse amplitude modulation, and then quantization is rounding off the amplitude of the pump signal, okay, in terms of flat top sampling, and to a finite levels, or in terms of finite levels, so that it is manageable. Okay, and then After that, these labels are converted in terms of code, means code depends on the number of labels, and through code in terms of binary bits, okay, encoded in terms of binary bits. So for the sampling, because there are 3 stages: sampling, quantization, error. We already discussed in previous lessons, sampling should follow Nyquist rate or Nyquist theorem, which is where Fs should be greater than equals to Fm. Fm is the information signal frequency, highest information signal frequency. But in case this one is less, means sample is taken less, okay, or few samples, there will be aliasing. So aliasing causes a new signal near the original to be created. And Fs minus Fm, this signal has the frequency and the aliasing, Fs minus Fm. When this sample signal is converted back to digital and then transmitted through the channel, and at the receiver, it's again reconverted back from digital to analog, the output will be different due to aliasing. Okay? Cannot be recovered as the take the approximation of original signal. So let's see 2 examples. This is Fs equals to Fa, means exactly all the minimum Nyquist rate, minimum sampling frequency. So they are back to back. Okay, Fs minus Fa. So is here is back to back. So Fs minus Fa, Fs plus Fa. Okay, and then 2Fs plus, this is 2Fs, 2Fs plus Fa, 3Fs, 3Fs plus Fa. So they are ideal, means back to back, touched, one sample is touched to another. So it can be recovered at the receiver side. But when Fs is less than 2Fa, I mean sampling frequency is less than 2 of our information signal frequency, you can see Fs minus Fa, there is not touch back to back. Okay, so they are overlapped. So this portion will be distorted. This portion, so there will be aliasing or the loss of the signals. Okay. So here also the another example. If less than, these are the distortion occurred. Here is a distortion or aliasing occurred, and there will be loss of the signal. Whereas if it is more, they are you can see the Fm, Fs, 2Fs, 3Fs, so there is a gap in between, so they can be recovered very easily. Okay. Now let us see in terms of some example and figures. Here in figure given analog signal, okay, the highest amplitude is 4 volt, lowest amplitude is -4 volt. The signal is then sampled by sampling pulses. So we can see the sampling. You can see there are so many sample space. Fs is greater than 2Fa. So the sampling is all right, no problem. So sampling means we are taking only the values. Okay, amplitude level here, pulse amplitude modulation. So amplitude sampling. Okay. Now quantization. So we will use linear quantization because we are focusing on linear PCM. As mentioned before, the quantization means all the sampled signals values are in terms of non-integer or the fractional value, or in terms of decimal value, which is we say analog. This we have to divide in terms of few levels. Okay, and all the values we have to express in terms of these levels and then in terms of bits. So usually how many bits we have to consider first, because the labels depends on that. So if there are n bits, okay, so there will be 2 to the power n labels, and then we actually, all the sample points we round off to fit into these labels. This process is called quantization. Now, if the number of bits considered is n, what is the number of labels? Labels can be expressed in terms of L or M, 2 to the power n. So, if n is 3, 2 to the power 3 means there will be 8. If n is 2, the number of labels will be 4. More labels, more accurate. Okay, the output. Accuracy will be more. Less label, the error will be more. Accuracy will be less. So for example, for a 3-bit PCM, there will be number of labels L equals 2 to the power 3 means 8. For 8-bit PCM, the number of labels L will be 2 to the power 8. Okay, now one more quantity we need to know, the quantization interval or resolution. What is the quantization interval? Means from one, since we are distributing all the values in terms of finite levels, what will be difference between one level to another level? That one, the quantization interval delta P, or it is known as resolution. So how we know the value of resolution or quantization interval? That one is maximum M minus minimum M divided by L. L is the highest voltage, lowest voltage. Okay. So let us see for this example, what is the interval? Okay, because this one equal interval we are discussing about. So since equal interval, here M max is 4 volt, M min is negative 4 volt. So how many levels will be there? Or what is the quantization interval or resolution? M max minus M min, 4 minus 4 means 8 volt divided by 4 is 2 volt. So this is our quantization interval. The minimum value in a level is 2 volt and 2 volt. Okay. Now, from that example, how we can get, because this is the interval. Interval means there will be 4 interval we have seen. So there will be 1 in between. There will be in between 1 means negative 2, 8, negative 4, negative 2, 0, 2, 4. Okay. So this is 2, 2, 2. Now, since we have done number of labels, suppose if n equals 2, 2 to the power 2 means 4 labels. So where will be label, and for 4 labels, the label will be started from 0 to 3. So where is label 0? Where is label 1, 2, 3? Eh? We have interval, we know, or resolution is 2 volt, but where will be the position of level number 1, level 2, level 3, 4? So that one we can find out. So the first level is 0. Okay, so for level 0, what will be the value of from where the level 0 will be started? So let us see this one V0, voltage level 0. So V0 means V minimum plus resolution divided by 2, or quantization interval divided by 2. Okay, so the quantization level value for the first one is this. So for the example, we discussed V min equals negative 4, delta V equals 2 is negative 3 volt. So our V0 is negative 3. So what will be the next? Vk means V1, V2, V3, V4. So V1 will be V0 plus delta V. Okay. Okay. And then V2, V1 plus delta V. And V3, V2 plus delta V. It's like that. So V1 means this one, V0 means negative 3 plus delta V is 2, negative 1. So what we can say from here? Okay. So what is the value of V2? Let us see. V2 equals V1 plus delta V. Okay, means interval. Interval is negative is 2 plus 2. So V1 is negative 1 plus 2. This one will be negative 1 plus 2 equals 1 volt. So this is V2. Okay, or we can say this is the V2. And similarly, we can say very clearly, okay, we can say what is the value of V3? V3 will be equals, V2 is 1 plus delta V is 2. So 1 plus 2 equals 3 volt. Okay, this one that. So we know for 4 levels, V1, V2 and V3. Okay, we have all the levels. This one the levels. So we can for many levels, like if 3 bit 2 to the power 3 8 levels, in this way we can calculate the values of all levels. So how this one will be, we can arrange. So for level 0, this one is -3, and we know delta V is 2 volt. 2 volt means it will be started from -4 to -2, in between -3. So -4 to -4. This is the at level 0, the range of voltage. Okay, voltage range, and the level marking is -3 volt, and so on. So we'll see next. How is this? Okay. I'm going for mouse. Now, let us make clear. We have 4 levels. We have 4 levels. Okay, level 0, level 1, level 2, and level 3. Have arranged within 4 different colors. So level 0 range is -4 to -2, because 2 volt. Level 1 range is -2 to 0, 2 volt. Means this is the interval. This is the quantization interval or the resolution. Level 2 is 0 to 2 volt. Level 3 is 2 to 4 volt. Okay, because our range is -4 to 4 volt. Now, level 1 is here, from here. This is our level 1. Okay, this is the level 1. Let me take the color. Color is a little bit different. Okay, so I'm redrawing it. This is the level 1. Sorry, the level 0. Level 1 is from here to here. This is level 1. Level 2 is this. This is the value of level 2. And level 3 is this. Okay, this is level 3. So range is this, and the level 1 value is -3 volt. Level 0 value is -3 volt. Level 1 value is -1. Level 2 is 1 volt. Level 3 is 3 volt. Okay, but the range is this. So if value is within this range, any value of the sampling like this one within this range, right? So if we will approximate the value or estimate the value as 3. This one also 3. This one also 3, 3, 3, all these 3. Okay, whatever the sample value within this range, 0 to 2, there will be level 2. So this is our level 2. Okay, and this is the range. So all this, and this, the value will be approximated to 2 volt. Okay. Similarly, within this level 1, like this value, okay, this one will be approximated at -1, because this one within this range. And then, okay, this one, okay, all will be approximated to this range. Now, from 2 to 4, -2 to -4, this is our level 0. So all the value will be approximated to -3. Means there are some error, right? We can see that the value is less or more. We are taking approximate value is -3 volt and so on. So there will be some error. These errors are known as quantization error. And all the values we are taking to the nearest value, nearest level, means in terms of the level value, means either 0, 1, 2, or 3, and the value we are taking in terms of that, this is the quantization. So, clear drawing. Let me clear up. Okay, so that we can go nicely. So the error, quantization error. What is the quantization error? The difference between an input value and quantized value, means actual sample value and quantized value. Like that. These are the values. What is the label? Okay. These are the values, actual values, but we have approximated this value is 3. Okay, as the label 3, means all this value within this range. So this is the quantization error, usually denoted by QE. So quantized value negative, the original analog signal value. Usually the maximum quantization error QE equals the resolution divided by 2. What is the resolution? Resolution means the quantization interval delta V. Here is 2 volt. So 2 divided by 2 means 1 volt. This is the maximum, because this cannot be more than 1. We can see from the figure. Okay. Now another one, how efficient the PCM code is, or the quantizer is. Okay, it means the digital to analog converter or analog to digital converter. How efficient is it? It depends on dynamic range. So dynamic range is Vmax divided by Vmin, or maximum value divided by Vmin. Okay, the voltage level, or can be Mmax minus Mmin divided by delta V. Okay, this is our the signal, maximum value, or information signal minimum divided by the interval, or 2 to the power n if n bits are used. So this one usually unitless and expressed in terms of dB, decibel value. So DR in dB means 20 log Vmax by Vmin, or 20 logs 2 to the power n. Okay, the quantum value, okay, this one minimum, this one the maximum voltage magnitude of digital to analog converter, and this one the number of bits used in PCM. So let us see one example. Suppose one information signal, analog signal, is given this. The arrows here are showing the sample taken. Okay, this is the sampling point. Sampling interval is from here to here, here to here, here to here. Now, what is the maximum value of the signal? We can see here 5 volt, whereas the minimum is -1, -2. Okay, so let us see how we can do this one. What is the L? How many levels we have to means arrange all the sample values in terms of levels. So how many levels? L. In this case, we are considering 3 bits PCM. So 2 to the power 3 equals 8. Okay. Now, as I mentioned, the maximum signal voltage level or amplitude is 6 volt and minimum is -2. So the quantization interval delta V equals 6, -2 divided by 8, 1 volt. Now, our first quantization level. So this one V0, Vmin plus delta V by 2 as per our formula. So -2, delta V is 1, 1 by 2, 1.5. So -1.5 volt. So what will be V1? V1, this one, plus our delta V is 1 volt. Okay, so -0.5, and so on. We can find out V2, just plus add 1, will be 0.5. V3, just add with V2, this one means 1.5, and so on until level 7. We can go and go ahead and calculate all the values. So let us build a table. In terms of table, is much more efficient, and we can actually clearly see how this is happening. So 3 bits, there are 8 level. 8 level is 0 to 7. So 0, 1, 2, 3, 4 until 7. don't worry, can arrange like this or can arrange 0, 1, 2, 3, 4, 7 also like that. Okay, this one no problem. Okay, now what are the range of voltage? In our case 1 volt, right? So -2 is the minimum value, -2 to -1, because interval delta V is 1 volt. Okay, minimum is -2. So it will be started from -2 until the maximum value 6 volt. So -2 to -1 interval, -1 to 0, 0 to 1, and so on. So we can see -1 to 2, -1 to 0, 0 to 1, 1 to 2, until 5 to 6. Our all similar. Now, what is the quantized level or quantization level, quantized value in which we will approximate all the sample value? That one we already get. V naught is -1.5, and V1 means plus add 1 volt, 1 volt, and it will go ahead. So first one is -1.5, -0.5, plus 1, 0.5, plus 1, 1.5, and so on until 5.5. So this table is the basic table. Based on this, we can approximate all the sample value. We'll check within which range, and from the range, we can get what is the quantized value. Okay, approximate value, and then we can convert in terms of level, and from the level we can go for the number of bits, binary code. That one I am showing later. So based on, if we actually continue, based on our this table, if we want to convert in terms of PCM bits, this one 3 bits, okay, this example 2. So 0 means 3 bits 0, 0, 0. 1 means 0, 0, 1, and so on. 7 means 1, 1, 1. So how we can rewrite this table? Okay, let's extend this one. We can then set the binary coding for this level. How is this? Okay, this is the binary. This is the previous one, our table. Now for 0, 0, 0, 1, for 1, 0, 0, 1, and gradually for 7 is 1, 1, 1. This is our complete table for conversion into pulse code modulation, or in terms of binary bits coding, okay, encoding. So this is the basic or main things we need to develop first. Okay, then it will be easy for us to encode the sample values from any signal. For example, let us see if the value is 2.35 volts sample value, what will be the level and what will be the PCM code or encoded bits. So let us go to the table. 2.35 is within this range. We can see 2.35. So the approximated value will be 2.5. The level is 4. 4 means the encoded bit is 100. Okay. So for each, like -1.4 volt, -1.4 volt is within this range, -2 to -1, means approximated value will be, or quantized value will be -1.5. The level of the code 0 means its value is 0, 0, 0. Okay, so this is actually how we can encode the values. So again, let us see how is the bit rate and sampling rate again. So sampling rate Fs is 2 FMN, as we know from Nyquist theorem or Nyquist rule. So the sampling rate we can find out 1 over Ts. Fs equals 1 over Ts. What is the bit rate? Bit rate is FB. FB equals Fs multiply N. This one we have learned in our previous lesson. Fs the sampling rate, N is number of bits per sample. Like for 3-bit PCM, there will be N equal to 3. Okay? So we can calculate that. For example, for the example 2 PCM 3-bit PCM system. So let's say If the highest frequency of analog signal FM is 200 Hertz, what is Fs? Fs equals 2 FM, minimum frequency, sampling frequency. 2 FM means 400 Hertz. So what is the bit rate? This is 3-bit PCM. So bit rate Fs into 3, 400 multiplication 3, so 1200 bit per second or 1.2 kilobit per second. Okay, now let us see. Find the sampling rate for PCM system described previously, means 3-bit PCM. If the number of bits per sample for the PCM system is changed to 2 bits or 4 bits, means now 2-bit PCM or 4-bit PCM or 8-bit PCM. So we can find out 2-bit means the n will be 2, n will be 4, and n will be 8. So for our previous example, Fs is 400 Hertz, and then bit rate will be 400 multiplication 2 means, let me write here. In this case, FB will be, because let me write here, our Fs was 400 Hertz. Just now we discussed. So what will be the FB? FB will be 400 multiplication 2 for number A. So it will be 800 bit per second. Okay, and so on this one. So we can see if the number of bits more, like for this one, 4 into 4 means 1600 bit per second, and this one will be much more. So if number of bits more, the bit rate will be higher, means system efficiency is better. Okay, but it will, number of levels will be also more, so accuracy also will be more, but complication will raise a little bit. Okay, if we can tolerate, we better to go for higher bit rate. Okay, so next. So our previous example we discussed 2 and 3. Now let us try to find out the quantized values for each sampled signals. For sampling rate, Fs equals 400 Hertz. So what is the sampling interval? Okay, of sampling period, Ts 1 by Fs, 1 by 400, 2.5 millisecond. Thus, at every 2.5 millisecond, we will capture one sample from the original continuous or analog signal. Now, let us see. This is the original signal. Maximum is 5 volt. Minimum is -2 volt. Just we discussed previously. So, if our sampling rate 400 Hertz, sampling interval is 2.5 millisecond. This one in terms of millisecond. So, how we will take the sample? You can see the first sample is here, second sample, third sample, fourth sample, and so on. We can go. After 2.5 millisecond, 2.5 millisecond, we can get a sample, and these are the sampling values. So, the table we developed for 3-bit PCM before, this is our quantized value, this is the range, this is the code, encode. Okay, we developed previously, and then we will go for this. Now, from the graph, sampling time is, or interval is 2.5 millisecond. So we can see 2.5 is, first value is 2.3. Second value at 5 is sample value 3.5. Let me show again. Okay, this one 1, 2, right? 2.3. Then second value 1, 2, 3. Okay, this one. So 3.5. Now 2.3 the which range? 2.3. Let us refer to this table. 2.3 is within this range 2 to 3. Quantized value is 2.5. And 3.5 is here 3 to 4. Quantized value is 3.5. It's the level 5. So this one quantized value 2.5. This one quantized value 3.3. This one level 5. So 1, 0, 5. But quantized value and sample value is same. So there is no error. Error is 0. Whereas this one sample value 2.3. Quantized value is 2.5. So there is absolute error is this one minus this one. Then we can take modulus. So 0.02. And this one, the quantization level is 4. 4 means 100. So we can clearly, this is the encoded value. So we can do for all sample values. Okay, what are the sample, all the sampling time. Here the sample values. Here quantized value. What will be the code? And then we can write the code in a series. This is the encoded bits. Okay, how much errors? We can also calculate. This is individual, for individual sample, the errors. Okay, this is, so far we discussed unfolded. Now for folded. The difference is folded and unfolded is the first level, 0 level is separated into 2. Okay, that one. So that's why from 0, there is one positive, there is one negative. Why? Because there is one bit reserved for sign value. Sign value means either it is positive or negative. The rest of the bits used for the labels. For example, if 3-bit PCM, first bit, the most significant bit will be reserved for the sign, plus or minus. So for plus maybe is 1, for minus it is 0. And then other 2 will be used for the labels. So there will be 4 labels. So 4 labels up, first bit is positive. 4 levels down, first bit is negative, is 0. Okay. So in this way, like 0, 1, 2, 3. 0, negative 1, negative 2, negative 3. Okay. This is the up for positive values. This is the downwards for the negative value. Since there will be 2 level of means for the 8, if we convert 0, 8, 0, 0, 0, then 1, 0, 0, 1, 2, 1, 0, 1, 0, 1, 0, 0, 1, 1. And here also is the same way. Okay. So 1, 0, 1, because first is the plus positive bits. That's why here 1. 1 is positive. This first is 0 is negative. So 2 bit 0, 0, 0, 1, 1, 0, 1, 1. Now here first bit sign bit is positive. So 1, 1, 1. Now 2 bit 0, 0, 0, 1, 1, 0, 1, 1. So 0 level voltage can be denoted by 1, 0, 0 and 0, 0, 0. That's the folded PCB. Now for 0, 0, 0, this one negative side. So the 0 volt, this range will be divided into 2. For 0 to negative and 0 to positive, the divided into 2. So positive side will be 1, 0, 0, negative side will be 0, 0, 0. That's the difference between folded and unfolded PCM. So let's see for the example for 3-bit PCM again, 1 bit for sign. So if 1, all 1, if 0, 0. Now the level 0, 1, 2, 3, 4, 5, 6, 7, right? So 3 and 4, these 2 is for 0 level. So 2 level reserved for 0. 1 is 1/2 is for negative, 1/2 for positive 0. Okay, that's so how the values are divided. 0 to 0.5, 0 to negative 0.5, and then so on here and here. Okay, this is the folded PCM. So this, if the value is plus 2.5 to 3.5, it will be plus 3. This is the quantized value, and this is the quantized value. And then level 7 means 1, 1, 1. This means positive. Here 1 means is positive. Like negative 3, If the value is in between negative 2.5 to negative 3.5, it will be quantized to or approximated to negative 3. This is the quantized value. It's level 0. 0 means 0, and the magnitude for this is 1, 1. So 0, 1, 1. So, but we are focusing here more on linear PCM. Okay, so that's for the folded 2.6 volt, the PCM code would be 111, while negative 2.6 will be 011. Okay, there are some exercise. Okay, now let us discuss about the dynamic range. As I mentioned, dynamic range indicates how good the system working, okay, or system efficiency. So for folded, VR equals, again, the definition is same, Vmax by Vmin, Vmax by resolution. But before it was 2 to the power n, for folded 2 to the power n negative 1, because 2 level is represents the same quantization level 0. Okay, that's why. So in dB, 20 log 2 to the power n minus 1. Okay, now coding efficiency. This is for both linear, folded and unfolded PCM. Coding efficiency is minimum number of bits used divided by actual number of bits multiplied by 100. This is the coding. So what is the minimum number of bits? If we calculate from the dynamic range, how the bit, a number of bits, because it can be fraction, but we cannot use fraction. We have to go the nearest integer values number of bits. That one will be the actual number of bits. So for example, let us see one example. This is a folded binary PCM. Don't worry, if it is not unfolded also, there will be not written anything, but it's the exactly same way we can calculate. Okay, so the one folded binary PCM system has the following specification. What are the specification? Maximum analog input frequency is 4 kilohertz, means FM is 4 kilohertz. Maximum decoded voltage at the receiver is plus minus 2.55 volt. This one the Vmax, and the dynamic range is given 46 dB. Okay, decibel. Determine the following: the minimum sampling rate. What is the minimum? It is easy. Fs equals to FM. FM is 4. 2 into 4 is 8 kilohertz. Minimum number of bits used in PCM code that we can use from here using this formula. Okay, because our dynamic range is given. Then resolution we can find out, quantization error we can find out, and coding efficiency also we can find out. Coding efficiency number of minimum number of bits divided by actual number of bits. Okay, so let us see first. What is the sampling rate? Fs equals to Fa. That one Fa is given 4 kilohertz, so 8 kilohertz. Minimum number of bits. So we have given the dynamic range 46. 46 is 20 log Vmax by Vmin. So Vmax by Vmin is, if we take anti-log, 46 by 20 to the 199.5. And this equals Vmax by Vmin. This equals 2 to the power n minus 1. So we can write here 199.5 equals this 2 to the power, or we can go from here also. Okay, is 2 to the, or this one equals 2 to the power n minus 1 because it's folded. So 2 to the power n equals 199.5 plus 1. So if we n means log base 2, or if log 10 divided by log 2. So this is the formula. So 7.65. If 7.65, okay, this is a fraction, right? Number of bits cannot be fraction. We cannot take 7 because it will be low. So approximate value or the nearest integer value is 8. So n will be 8. Okay, now the resolution. What is the resolution? Resolution can be defined by Vmax divided by 2 to the power n minus 1. Why? Here. Okay. So if we go from here, Vmax divided by 2 to the power n minus 1 equals resolution. N value we know. So Vmax also given. We have given in the question. So we can, because 255 volt, this one given. Okay, so we can very easily find out 2 to the power n minus 1. N value is this. Okay. Okay. So we can calculate from here the Vmax divided by 2 to the power means 0.01 volt. This is the resolution. Resolution means delta V. Okay. So what is the quantization error? Maximum quantization error is resolution divided by 2, right? We discussed. So this one divided by 2 is 0.005 volt. This one the maximum error. Okay, now coding efficiency by definition. Okay, minimum number of bits divided by actual number of bits. Minimum is 7.65, actual is 8. Because we cannot use 7.65 or 7. Multiply by 100, so 95.625%. So this is actually the coding efficiency. Okay, DR is the this is the formula. From here we use all this. Okay, so this is how we can solve. Now let us go for the summary. Summary is for 3-bit PCM, we have to first calculate what are the number of levels. 3 bits, 2 to the power 3 means 8. So there will be 0 to 7. And what will be the code? We can. Now, I didn't put here the full table. Always we have to develop the full quantization table in terms of levels, in terms of quantization, quantized value, the quantized level, then quantization range, and the code words. Okay. After that, we have to get the sample value from the our original signal or analog signal given, like input signal. This is the sampled values. Okay, this is discrete values, but still a fractional value. These are the values what we have to see in which it match with which level, and then what are the encoded values. So the encoded value can be like this one, 7. 7 means is level 7 already. Okay, because 6 to 7, so 7, 1, 1, 1. So that we can get the value. Okay, first one we can see the value is 5. Okay, 5 means this is within this level 4 to 5. So we can see the label. I put here the label. So it's the 5. 5 means 101. You can see 101. Then 7, 111. Then 6, 110, 110. Then there is 3. Okay, because this one more than here, right? So this one 1, level 1 here. So 1 means 001. And then this one is level 2. 2 means 012 and so on. So total here, how many sampling points are taken? 10. For 0 to 10 means 11. 3-bit PCM, so 3 into 11, there will be 33 bits. We can see all the 33 bits are here used to encode this, actually this portion of the signal. Okay, that for this signal. So that's all. Let's again another one, again summary. Okay, what are the sampled values? Sampled values can see from here is sample. Okay, first sample, second sample, third sample, fourth, fifth, sixth, seventh. Okay, and then this is the sampling interval. TS is 1 by Fs or 1 by 2 FB. This is the time. This is the code number, because we have 4-bit sampling. One example, 4-bit sampling. 4 means 2 to the power 416. So number of levels 0 to 50. And then normalized magnitude means quantization level or quantized value, where we'll get the approximate of the sample value. So also they are 0 to all the 16 level values. So palm value, Here we can see the quantized value, pulse amplitude value, and pulse code modulated or encoded PCM code. So pulse value, pump value is amplitude, just the sample. First sample is 1.1. But this one will be quantized number is 1. So 1 means in terms of 4-bit 0001. Second one is here 9.2. So it will be approximated to 9. 9 means this one. Third one is 15.2. So it will be 15. 15 means 111. Okay, this is on the 15, level 15, what I'm saying. This one the code number, this one the level. Okay, and so on. Okay, so we can see clearly what is the pump. Pump is the digital discrete value, but in terms of decimal points, means still the analog part is there. We can see is in terms of decimal, and it can be in terms of so many levels, 0.1, 0.1, 0.1, and so on. But we have to means arrange all this value in terms of finite number of labels instead of infinite. That one is the quantization level, and how we do that, that one is the quantization. Okay, using the quantizer. So here there are 16 levels, 0 to 15. In between, one is 1 volt, 1 volt. This is the quantization interval. So in between this, and then we can, according to the quantization means the code number, we can convert the value, sample value, pump value in this, in actually integer values, and from there in terms of code. Okay, encode in terms of binary bits. So that's the summary, and then there are 2 homework. You can try yourself, do yourself. So that's all today. Thank you. Stay tuned. So our next class will discuss on line coding. Okay. See you. Bye.